Our next paper is called Variational Low-Rank Multinomials for Collaborative Filtering with Site Information, and presented by Ehtsham.
Hi, I'm Ehtsham from Netflix, and this is joint work with my colleagues Wang, Aish, and Tony. So we call this like set of models that we develop, variational low-rank multinomials. Before you say that, oh no, you're doing the filtering method, I would like to highlight like the things which are not specific to this model, but are generally applicable to other techniques as well. So that would be my goal of this presentation. So imagine a data scientist. So basically, like we started working on this approach by imagining the role of a data scientist while solving a recommendation systems problem. What are the key things that are challenges in such problems? So the setup is very basic and traditional, and I think everyone is aware of this setup. So we're given a clean data set of users and movies. So some of the users, like they have played some movies, and then we do not know their preferences for the others. And then we call these as clicks. So clicks can be viewed as draws from a multinomial distribution, a user-level multinomial distribution. So basically, you can imagine that for each user, you roll a dice, and then the face which comes up, that basically corresponds to the movie that the user would watch. And then the goal is to learn those multinomial distributions. For some reason, like the text is, so the goal is to learn those multinomial distributions. So we always think that there is lots of data, and in traditional collaborative filtering data sets, we have millions of users and thousands of items, but each user only interacts with a small number of items. So basically from that perspective, it's not really a big data problem, it's a small data problem. So there's lots of sparsity, and that sparsity should induce some uncertainty in the answers we give. For example, if you want to predict the probability of the user playing the things that they have not played before, our answers should include some form of uncertainty, and we should hope that, that uncertainty is kind of inversely proportional to the amount of activity those users have. So for example, for the top users, in this try example, for whom we have more information, our answers should be basically like, it should contain narrower variance, whereas for the bottom users, they should contain bigger variances. These are just like try examples. Another thing that we may want to take into account is the cold start of new items. For example, the third item in this try example, it did not have any user interaction. So, but we may have some extra information or side information for all the items, basically like the metadata and tags. So we may want to incorporate those that side information, but still do like inference with these uncertainty estimates, and the natural way to handle that uncertainty estimate, if you haven't like guessed it already, it's using Bayesian inference. So basically, the summary is that we want to do this, we want to solve this traditional collaborative filtering task by incorporating tags and metadata of items to handle cold start, and also like do Bayesian inference because like there's lots of sparsity, and we want to use that information to induce uncertainty in our answers. So the details of the model are actually not that complicated. So we basically assume that we have some uncertainty about our user preferences, so that's the core idea. So essentially we put a prior over user preferences, and that prior flows through our user-movie interaction model, where that distribution interacts with, you can imagine there are some parameters specific to these movies, so interact with those parameters to produce a score which is then transformed through the softmax, and then you get it, and then outside you get a multinomial distribution, and not just a single multinomial distribution, but rather a distribution over those multinomial distributions, because the input itself is a distribution. More specifically, we basically use a low-rank representation for the user Z. The low-rank factor is ZU, which is generally, we generally note it as k-dimensional, and it has a normal prior, and it flows through the user-movie interaction model, which in this case we have chosen to be something very simple. Just to highlight the case, although it could be something that you would design for a task, but these bilinear simple models, they get retained faster. So just to describe the two components in this model, ZU is the user level latent factor, and then the item component has two parts. One is B, which is traditionally like the traditional item factors, latent factors for the items, and then a matrix G, which are the latent factors associated with tags, and then that matrix G basically linearly combines with this metadata matrix, which is given to us. It's the data matrix, so which basically tells like which movies have which tags. And so basically, like these two components, they form the item representation, and then you take a simple inner product of that item representation to the user factor to get a score over the entire like, sort of items, which then gets transformed to softmax. So given such a model, the goal is to learn the unknown parameters, which in this case are the matrix P, G, and most importantly, we want to learn the posterior over Z. Which is basically like where we invoke the variational approximation, which I'll just go in detail now. So as I think it would be evident, the exact posterior in this case is analytically intractable, and the reason is quite simple. That we're using a likelihood which is softmax, and then the priors for the user-linked factors are normal, and the combination is intractable to normalize. So to solve this problem, we basically assume that we take the posterior variational approach, where we assume that the posterior has some known form with unknown parameters, and we take that form to be the same as the form of the prior, which was the normal distribution. So in this case, variational approximation is a k-dimensional Gaussian which has a mean and a scalar parameter for variance. So basically, we have introduced one additional parameter. So traditionally in maximum likelihood estimates, you would solve directly for Z, but here, instead of solving for Z, you solve for a distribution on Z, which has a mean vector mu and a single scalar parameter. So it's basically like an anisotropic Gaussian to capture the uncertainty. So basically, we haven't added a lot in the model, but one additional parameter per user to capture the uncertainty. So even with this variation approximation, the first thing is like the variation objective, and the second component in that variation objective is the expectation of the log likelihood, and the expectation is being taken with respect to the variational distribution, which I just described as a normal distribution. So even with the variation approximation, this expectation is intractable for the same reason that the log likelihood is softmax. So the standard trick is basically to re-parameterize this expectation using a source of randomness which is known. So compared to the previous expectation where the source of randomness is unknown, it's an unknown distribution, you re-parameterize using the inverse CDF of Gaussian distribution so that the source of randomness is a standard normal. So what that does, it basically decouples the source of randomness from the parameters that you want to approximate, in this case mu and sigma. And then what you can do, you can basically take an MCMC estimate of this expectation, and this MCMC estimate is known to be of low variance. So with these set of transformations, you have a new variational objective function which is stochastic because you're doing MCMC sampling to compute the expectations. And now you can optimize this re-parameterized objective using any gradient-based technique. People generally use SGD or ADAM for these tasks. We also tried using like an old school conjugate gradient approach, and I'll describe the results for both of them. So that's basically like the details about the model. Now I'll try to focus a little bit about the insights that we got from this model. First of all, that does it really work? And here I've shown two plots. The left one is using ADAM to optimize the variational objective, and the right plot is using conjugate gradient. So the first plot basically is showing the convergence of ADAM with the number of equations, whereas the right plot is showing the convergence with the number of samples which are needed to compute the gradient. And in both cases, we see that, in a few hundred iterations using ADAM, where essentially you're sampling you're using like one sample per iteration to compute the gradients. It converges like in a few hundred iterations. And in conjugate gradient, where you run the conjugate gradient to convergence, but you compute the gradients using fixed number of samples. It means like only 50 or 60 samples to get its best performance. So the thing which motivated us to take this Bayesian approach, and I mentioned that it's really like a small data problem, was the sparsity. So does this approach handle sparsity? So this plot is essentially showing like what we learn in our variational distribution. So the left plot is the variational standard deviation, and I'm plotting that against the length of the observation vector, that is like how many observations we have for that user. And we see that the learned variational standard deviations, they have this nice like exponentially decaying form, which matches our intuition that as we get more data, the standard deviations should fall down. Whereas this right plot is basically trying to capture or measure how much information we have in the mean of the variational distribution. And one way to measure that is to compute the norm of that variational mean, and we see that the norm is positively correlated with the number of observations we get for that user. The third thing which I mentioned was that does our inclusion of metadata, does that handle or help our case of item code start? So here there are two plots. First I'll try to describe the right one. So we want to simulate the case that, simulate the use case of cold starting. So basically what we did in this experiment, we censored out a small set of items from our training data set and then pretend that those are items which are cold starting. And then we also divide those items in terms of their popularity in the original uncensored data set. And we try to see like whether including tags or not including tags helps. So the blue bars are for the model which doesn't include tags, and the brown bars are the one which uses tags. And lower is better because I'm showing average ranks. So basically what it is showing that for cold starting, the model is able to predict items at all popularity levels. On the left side, it's the same setup, but here these items are present in the matrix, like they're not cold starting. And here we see that the tags don't add too much, and user interaction data is quite sufficient to do good for items in all popularity levels. I'll try to highlight like a little bit about the numerical evaluation because obviously it needed to do well as well on the standard open source data sets that we traditionally use in conferences like RecSys. So we tried using this model on movie lengths, Netflix, and minutes on data set. And then the evaluation metrics we used were traditional like top end evaluation metrics like recall and NDCG. And you can see the detailed results in the paper. But the summary is that the model is quite competitive compared to the various popular baselines like SLAM, weighted regressive factorization. And LDA, we included LDA as well because we were trying to model a setup which involved categorical distributions. And then we also compared the model against its non-Bayesian version, where we basically don't try to estimate the variational distribution, just try to get the point estimates. It improves quite significantly over the non-Bayesian version, which basically suggests that all the handling of sparsity does add up in terms of accuracy as well. So just to conclude, so basically what we did, we combined the modeling flexibility of factorization style techniques with Bayesian inference. So when people think about Bayesian inference, they generally think that it's a computationally very hard thing to do. But in this presentation, in this work, we were able to use variational inference with the re-parameterization trick, which has recently been popularized in deep learning as well. Which makes approximate Bayesian inference in these kind of models actually quite easy, and it doesn't add much to the cost. And I suggest, if there's one takeaway from this paper, I would suggest that you give variational inference with re-parameterization if you have models of similar flavor.
Is there a question?
Thanks for the nice talk. I had a question about scalability. So the log likelihood function is the, softmax. Is it over all the items? Isn't that problematic in the sense that a single observation touches all the embeddings?
Yeah, so for certain kinds of data set, the vocabulary or set of items which are present could be too large and we may not be able to compute the exact softmax, and then there are approximation techniques. In this case, in these three data sets, the item sets are not that big, so it was not a problem. But yeah, it definitely is a problem when you have data sets with, and I think the Google talk before us, I think something.
Thank you.
Other questions? There's one over there.
Thank you for your talk. My question is, which specific site information have you used in your dataset, and is it possible to integrate textual information in your model?
Yeah, so as I mentioned, So generally, like, I mean, those movies, they come with some tags, and those tags could be derived from textual information as well. Here I was using like a very simple bag of words kind of assumption that each movie, it may have these tags which themselves can be assumed to be some, basically coming from some multinomial distribution. So yeah, so like, I mean, you can, like, I mean, have those metadata coming from text as well.
Thanks for the talk, it was really interesting. I think regarding the fact that using Bayesian methods, you are basically getting the variance as an output for pretty much for free. And are you using this subsequently in any other way, like particularly say using a per term diversion for mean plus variance to generate more data for the missing estimates and so on and so forth?
Yeah, so while computing these metrics, I was basically just taking the expectation of the score function that I had with respect to the variational distribution, which in this case, since it's a simple model, the expectation directly goes onto the random variable and essentially just use the mean of the variational distribution to compute the scores, and that was what I was using to compute the metrics. But yeah, you have like a lot more information, and one interesting thing that you can do is what you suggested, or like explore, exploit, and those kind of things.
Thank you.
Any other questions? Okay, thank you very much.